rescue. Respond to 723 Pine Street, cross street of Washington and Lake. Building fire, multiple calls. Attention Station 1, Station 2 rescue. Respond to 723 Pine Street, cross street of Washington and Lake. Building fire, multiple calls. 2124 operator.
EMS Unit 52, respond to victim of violence. Reported stabbing. 2371 Park Circle, cross street Atlantic Avenue. PD is on scene. EMS Unit 52, respond to victim of violence. Reported stabbing. 2371 Park Circle, cross street Atlantic Avenue. PD is on scene. 2128, dispatcher 112.
Welcome to Radio System Operation for Public Safety Communications Professionals. Although there are many different radio systems in operation, many of the control functions and systems operate with similar characteristics. There is transmit audio, method of activation of the transmitters, and receive operation. With a general understanding of these functions, you may be able to provide better service to the first responders that are receiving your dispatch traffic. The information on this video assists you in identifying or mitigating an equipment or system problem and will help you get your message out to your first responders. Let's go over the basics of equipment. There are multiple pieces of equipment that make up parts of your radio system. These include subscriber units, infrastructure equipment, and dispatch console equipment. Let's start with subscriber units. These are the devices that are used to communicate between other subscribers or with infrastructure equipment to a dispatcher or other fixed location. These include portable radios, mobile radios, desktop radios, and subscribers that can be remotely controlled called control stations. Subscriber radios come in many makes, models, shapes, and sizes. Portable radios are typically handheld radios that are carried by the first responder. Sometimes these are known as handy-talkies, handhelds, and they've even been known as miniatures. Mobile radios are typically mounted in a vehicle. A vehicle-mounted radio usually has a better antenna system than a portable radio and perhaps operates at a higher power. This offers an advantage over the portable, but requires the first responder to be at the vehicle to contact other users or a dispatcher. Vehicle-mounted radios usually come in two different forms. A dash-mount radio has the control head and microphone attached to the radio chassis. The advantage is that a dash mount usually has minimal cabling requirements and is a quicker install. Another choice is a remote mount radio. In this configuration, the control head is located near the vehicle operator and the radio chassis is installed elsewhere in the vehicle, usually in a trunk or a radio compartment in a larger vehicle. The control head is connected to the chassis by use of a control cable. Because the control head is relatively small, it can be mounted in tighter spaces, especially when other equipment is installed in the user area. The actual radio chassis can be mounted in other areas of the vehicle, usually the trunk. Sometimes a desktop radio is needed. A simple desktop radio can be made from a mobile radio mounted with a power supply and connected to an external antenna. These may be used in fixed locations like a police station or firehouse, where a user may need to contact units in the system without dispatcher intervention, or perhaps as a means of system monitoring. Depending on your system configuration, a desktop radio could be used as a backup to the dispatch system in case of a console failure, or as an alternate dispatch location for redundancy. Subscriber radios are generally selected by an agency based on operational needs and on cost. An agency operating in a metropolitan environment may select a radio with better filtering so the user can have an improved performance while working in an area where there are a lot of strong interfering signals. This may increase the cost of a subscriber. Other groups within an agency may work in a tactical manner and might need less power to communicate amongst themselves. The lower power radio may provide a cost savings. An agency may hire a radio system consultant or have their own engineering team assist in the selection of subscribers based on costs and expected performance. Infrastructure equipment is the backbone of the radio dispatch system. The equipment is comprised of base station radios, antennas, connections from dispatch console equipment, and other fixed location equipment that is installed at the point of dispatch or at remote locations away from the dispatch center. Infrastructure equipment and configurations are as varied as the users that operate them. There are conventional systems, trunked radio systems, and P25 systems, just to name a few. We will examine their operation methods later on. Dispatcher equipment is the user interface to the infrastructure equipment. Whether the connections are circuit-based, IP-based, or connected by some other method, the dispatch equipment at the most basic level transforms electronic signals into audio and/or visual indications that can be used by a dispatcher. Let's review some system and interconnection basics that will help you understand the various interconnections that connect your system or systems. Radio systems can operate in a conventional mode or trunked mode, and they can be analog or digital. Base station infrastructure equipment is usually installed where there is an equipment room or shelter with adequate power and security for the equipment, with the antennas installed at high locations to provide maximum coverage, typically on a tower or building rooftop. The antennas are connected to the base stations using coaxial cables. Let's look at our base station. Here is our basic transmitter and receiver. This equipment is usually within the same cabinet and maybe even in the same chassis within the cabinet. Our dispatch console is located in a PSAP or other dispatching location. Dispatch console equipment can be connected to base stations or other infrastructure using various connections or signal transport methods. Radio tie lines are telephone lines that are connected in a special fashion where it makes a direct connection between the dispatch center and the base station. An RF or radio frequency link, such as a microwave connection, can also be used as a transport method. Equipment connections can be through the internet or through an agency's intranet, an internal IP-based network, or by any combination of these or variations of wired and wireless transport methods. The conventional systems to be discussed will be general in nature and not vendor-specific. We will discuss typical practices and provide general overviews. Please check with your technical support team to determine what applies specifically to your system. We will also refer to all public safety telecommunicators, fire alarm dispatchers, police communications technicians, or other similar providers using the generic and familiar term of dispatcher. Conventional systems are typically single-channel systems. An agency may have multiple frequencies from which they operate, each supporting a different user group or operation. Police may operate on one channel, fire on a second, and EMS on a third. Multiple channel systems like trunked radio systems will be discussed later on. Let's discuss conventional systems, simplex. The simplest of the conventional systems would be a single frequency or simplex system. Simplex systems use the same frequency to transmit and receive on. In order to provide the best coverage over a large area, the antenna used by dispatch is located at a high site or on a large structure. The base station is located near the antenna and is connected usually by a coaxial cable. Typical base stations and connections to the antenna are seen here. This coaxial cable has a radio signal lost and should be kept as short as possible, which is why a base station is usually not too far from the antenna. The base station may be directly located at the dispatcher position, with the antenna connected to the base station. Small stations, generally known as control stations, are many times used for this purpose. If the base station is at another location, the base station may be controlled remotely in a way that was discussed in System and Interconnection Basics. One of the benefits of a simplex system is that there is no infrastructure between the subscriber unit and the base station. If you have the station at the dispatch point, you have no site maintenance concerns. The base station transmits to the subscriber and vice versa. A disadvantage to a simplex system is that both the base and the subscriber need high power if you are to attain good radio coverage. Portable radios may work, but there's usually much less coverage, so mobile radios are typically used. Sometimes, depending on your geographical area of coverage, other subscribers may not hear a subscriber talking to the dispatcher. If they were to transmit at the same time, this may interfere with each other. This would be heard by the dispatcher because the user signals are competing with each other. Unless one is significantly stronger than the other, neither may be understood. If one subscriber does not hear the other, there may be less situational awareness requiring the dispatcher to repeat the message traffic for the benefit of the other subscribers. However, simplex is very beneficial when units are operating in a tactical manner. This is the operation of choice for many fire departments when operating at an incident scene. There is no infrastructure needed, and the units can communicate locally with each other. Communications to dispatch is normally handled by a communications officer or the officer in charge, and is usually not on the same frequency that is used for the tactical operation. We will now discuss conventional systems repeaters. There are many benefits to using a repeater. A repeater station will receive on one frequency and retransmit the audio signal out on another. Using a repeater, you could still have a direct connection to the base station by the dispatcher, allowing a subscriber to be received by the dispatcher. The repeated signal would also be relayed to the other subscribers within the range of that repeater. The direct connection provides supervisory control of the base station. Depending on the configuration, a dispatcher may be able to enable or disable the repeat function, change channels, or take priority over the channel if, say, a subscriber was stuck in transmit, like a defective radio or a stuck microphone.
Citywide. Watch your portables.
If your agency has multiple locations that need to access the system, control stations would be a good choice of equipment for this purpose. These standalone stations are effectively desktop subscribers, perhaps a mobile radio using a 12-volt DC power supply, or a station specifically designed for this purpose. They don't have supervisory capability because they're linked by radio and have no direct connection to the base stations. Because you're talking through the repeater and not directly from your radio to the users in the field, the antenna can be of a higher gain and directional, aimed at the repeater site location. They usually don't need as much transmit power as a mobile subscriber because of their fixed location and gain antenna, and generally don't need as much power as if they were talking directly. Control stations could be added to an agency's backup plan. In case of a failure of the dispatch center, and as long as the repeater is operating, the control station can be used to contact the subscribers until the dispatch center can be placed back in service. Although the repeater provides these added benefits, because it operates from a single location, subscribers need to be mobile mounted and of higher power, unless it's over a very small service area. We will now discuss conventional systems voting receivers. Systems designed for mobile subscribers may operate satisfactorily with a single site. However, when portable radios are used, the single site may not be able to receive the low-power subscriber. So, how can a system be improved to support the use of the convenient portable radio? by adding additional receivers. These voting receivers are then connected back to a comparator, a device that monitors the quality of each receiver and then provides the best selected audio, also known as voted audio, to the dispatcher. Once in operation, received signals may be received by one, a few, or all of the receivers. The comparator will provide the best received signal to the dispatcher. This alone would greatly improve dispatcher received signals for a simplex system, but comparators can be configured to provide repeater operation also. Therefore, the weak portable transmitted signal received by even a single voting receiver can be retransmitted through the comparator to the base station out to the other subscriber units in the field.
Set up on the 39th floor. I have no injuries to report. Potential remains moderate to public safety personnel and civilians.
Of course, the number of receivers hit depends on the location and transmit power of the subscriber and the location of the receiver antenna. Conventional systems, multi-site, multicast. So, what if a unit is operating within its service area, perhaps is using a system with voting receivers, but cannot hear the dispatcher due to the distance from the base station? The answer may be to use multiple sites and operate in a multicast mode. This approach requires another base station at another location and another frequency that will provide coverage within that service area that was not covered by the other transmitter. This approach requires the field units to understand their radio operational area and know where and when to change channels. The dispatcher would transmit over both transmitters at the same time. When the subscriber field unit transmits, it would be received and repeated only over one system unless their receivers all came into one comparator. The comparator is not a radio, but an audio routing device, and it doesn't care what channel the audio signal comes in on. It is just interested in audio quality and providing the best audio signal. In this case, the field unit is transmitting within the west service area and is only being received by the west receiver. However, this comparator is configured to allow both the west and east transmitters to retransmit the voted audio. The comparator will vote on the incoming signal and retransmit it out over both transmitters for the benefit of all users, no matter what channel they may be on. With a multicast system, there is usually a bit of coverage overlap where either channel will work. Because of the different output frequencies of the base transmitter, there would be no interference between transmitters in areas of overlapping coverage. In addition to the improved coverage, another advantage of this system is that you have limited redundancy in case something happens to one site. You may have reduced coverage if one site is out, but as long as all subscribers have the channels in their radios, they all may have the capability to use the other available site or sites, especially if operating in overlapping transmitter areas. A disadvantage of multicast operation is that the user would have to switch channels to benefit from the improved dispatcher signal. If the user forgets to switch, they may end up operating outside the range of the system and lose contact with dispatch. In some cases, the frequency selection can be done through an automatic process like scanning or steering, but that is beyond the scope of this training video. Another significant disadvantage is that you need multiple frequencies to support this. In areas where frequency availability is limited or non-existent, you may not be able to obtain another frequency or frequencies to design this type of system. Conventional systems, simulcast. A multicast system requires more than one channel, and the user's radio has to be able to follow that channel and frequency somehow, by physically switching, scanning, or some other method. So what if there are no other frequencies available, or if you don't want the subscriber to have to change channels? A simulcast system may be the answer. A simulcast system is designed to cover a service area using multiple transmitters with all sites operating on the same frequency. The benefits are many. The user can operate throughout a service area without changing channels. Fewer channels are needed because the same channel is used over and over again. If there is base transmit power limitations in certain areas, additional sites can be designed in to provide good overlapping coverage. There is readily available redundancy. All transmitters are on at the same time, so if one fails, you may still be able to operate with slightly reduced coverage without user intervention. The disadvantage is that there is higher maintenance. There are usually more sites, more equipment to maintain, and they are technically complex. The transmitter frequency must be highly stable, and this is usually done with a highly stable reference oscillator or through high-stability GPS receivers. Timing and reliable connectivity between sites is essential. Audio phase delays must be designed so that the signal arrives at overlap locations at the same time, and that the audio levels are consistent. Differences in audio phase and amplitude cause distortion in the received signals. Trunked radio systems overview. If you have a group of frequencies available and are having trouble obtaining additional frequencies, or are interested in maintaining access control and preventing unauthorized access, or in having automatic redundancy in case of a base station failure, then a trunked radio system may provide the most efficient service. Let's say you have 5 conventional channels with assignments such as PD North, Fire Borough, EMS, a PD South channel, and a county-wide fire channel. Perhaps you'd like to split the fire boroughs into a north and south configuration, but don't have any additional frequencies. Maybe you're having a special event and it would be helpful to have a channel dedicated to that event, or for logistics use, or both. However, there are no additional frequencies available. Or the special event is a once-in-a-while occurrence where having a dedicated channel permanently would be of limited value during normal times and otherwise a wasted resource. Combining channels into a trunk system could provide you those additional resources when you need them without an increase in the number of channels. The trunking concept is based on the idea that not all users need to access the channels at the same time. Any idle channel is available for any user. This provides for a more even distribution of traffic over all of the channels. The users can be distributed among the channels without the user having to physically change channels. Trunked systems use logic control methods to allow users to access the channels. These control methods allow only authorized radios to access the system, assign or authorize a channel for use, monitor for emergency signaling, and hold a radio in queue for the next available channel if the system is busy. There are 2 types of trunking, centralized trunking and decentralized trunking. A centralized trunked system assigns one channel to act as the control channel. This channel provides all data to radios on the system. Due to the interconnections needed, the equipment in a centralized system is usually in the same physical area. A decentralized trunk system uses all system channels to provide data and does not need a control channel. Each radio is programmed with a home channel. The radio's assigned home base channel will provide the information as to its activity status and to what channel to go to when needed. The base station equipment can be in different locations, but needs to be interconnected so that data can be shared among each station. For our discussion here, we will refer to the centralized model for the more detailed explanations. However, many of the concepts can be applied to both types of systems. Because trunked radios use all assigned radio frequencies, users do not select a channel or a frequency on a radio, but they select a talk group. This talk group is effectively a digital channel. The controls on the subscriber radio act and feel like regular channel changing controls to the user. All radios on the same talk group can communicate with each other regardless of what frequency they are operating on. The system handles all frequency or channel selection. Trunked systems, single site. On a centralized trunk system, it was mentioned that one channel is assigned as a control channel. This control channel is the channel that all trunked radios look for when the radio is turned on and a trunked talk group is selected. All radios communicate with the control channel to obtain information on what it should be doing. Shall I wait idle? Is there other users on the talk group that I am on? What channel are they operating on? Am I authorized to even be operating on this system? Let's review a typical setup. Let's stay with the idea that we have 5 channels assigned to the centralized trunk system. A trunk system may have more than 5, depending on available frequencies and expected system performance. We'll have channel 1 stay the control channel. The control channel is handshaking with every radio that comes on the system. The subscriber makes contact with the system knows you're here and what talk group you are assigned to, and your radio receives an acknowledgement back from the system. Other users access the system in the same way and sit idle until someone on their talk group has activity. Let's say a few subscribers are on the system and a call is made from one user to another on the same talk group. When a push-to-talk is made on the microphone or handset, the radio transmits this request to the central controller. The controller looks at all of the activity on the system and assigns an available voice channel to the group and tells all of the radios on that talk group to go to that voice channel. All of the radios on that same talk group move and hear the traffic.
Thank you.
When the call is complete, all users go back to the control channel and listen for the next assignment. The time it takes for the initial call setup is about 250 milliseconds or a quarter of a second. If you operate a conventional system using identifiers at the beginning of the transmissions, the users may already be familiar with waiting before speaking and should not feel any difference between systems. However, this may take some getting used to by users coming from regular conventional systems with no IDs. As the control channel is important to the entire operation, systems are designed to have other channels operate as backups. If the first control channel fails, the system should automatically fail over to the second channel. A trunked system has the potential to have too many users accessing the system at once and have no channels available. If this occurs, the user will receive a busy signal. Centralized trunk systems will store the busy user's trunked ID in a queue of first in, first out, and then give the next available channel to that user. Priorities can be set for each user and group on a system. Perhaps police and fire users may be given a higher priority than a parks maintainer. If this was the case, if all of the channels were active and a fire user was making a call, then the lesser priority user, in this case the parks maintainer, would be dropped and sent back to the control channel awaiting another channel assignment. The fire user would now take that available channel for the call. Once another voice channel is made available, the lower priority user would get that channel assignment. Trunked systems, other features and configurations. The available features and configurations of trunk systems vary widely. You will need to consult with your radio system vendor or system maintainers to advise what particular features and configurations are used or available in your own system. Trunked systems can be set up to operate in message or transmission trunking configuration. Message trunking will keep the assigned channel available for a short preset period before returning it for reassignment. This allows a unit to provide a response to the initial call without having to go through the call setup and channel assignment process. Message trunking allows for a better communications experience for that particular user at the expense of keeping that channel unavailable for other users. In transmission trunking, the initial radio call is set up as normal. However, transmission trunking requires each transmission to go through the call setup and channel assignment for every transmission. This makes sure that each call is handled in a first-in, first-out order. Transmission trunking offers better channel availability for the system as a whole, providing more opportunity for other users to get a channel grant quicker. A centralized trunk system determines channel assignment and assignment order through the use of a site controller. The site controller is critical to the operation, and there's usually a redundant site controller available in case of failure of the main controller. The central site controller is usually located near the base station equipment and is wired into each station, providing direct control of each station. The central site controller selects which station is a control channel, monitors stations for receive activity, places defective stations out of service, along with other monitoring and control functions. Because the central site controller is critical to the operation, redundant controllers are usually used. However, if there was a failure of a site controller and any other redundant controllers, the working trunked base stations would resort to a failure mode known as failsoft. Failsoft would put each base station into a standalone operation that is similar to a conventional repeater operation. However, the transmitters would stay keyed, and there's usually a low-level beep in the transmission to let the user know that they are operating in a non-normal condition. Some radios are capable of displaying failsoft in their display, if so equipped. Subscribers that are critical to the operation would be programmed to operate in failsoft and would be assigned one of these channels. This is the last resort to keep communications available. If that base station fails, then those subscribers programmed to that failsoft channel will lose all communications. Subscribers do not need to operate in failsoft. If you have a large number of users and some of them perform tasks that are less critical, these users can be configured to not operate in failsoft, leaving the higher priority users to operate on the failsoft channels. This reduces the on-channel congestion that would occur if many groups operated on that one channel. Trunked systems can operate in a simulcast configuration. Like conventional simulcast, this allows for frequency reuse over a larger geographical area. System designs usually incorporate multiple levels of controller redundancy at a central level, controlling all of the sites, and at the individual site level. The level of discussion needed to describe these configurations in more detail is beyond the scope of this video. However, if you are operating a trunked simulcast public safety grade system, you most likely have redundancy at a centralized location as well as at each site. Check it with your system maintainer to verify. Narrowbanding overview. Narrowbanding requirements affect public safety users who operate in certain frequency bands, generally 150 to 174 MHz and 450 to 512 MHz. The intent of narrowbanding is to gain additional frequencies by reducing the bandwidth of a licensee's transmitter signal. Transmitters were licensed for use with a 25 kHz bandwidth. The FCC narrow banding mandate requires this bandwidth to be reduced by half. These 12.5 kHz channels would now make spaces for other licensees. The process began in 1991 with the FCC requiring all equipment vendors to make radio equipment capable of 12.5 kHz operation by 1996. As equipment was expected to be replaced over time, the FCC presented certain deadlines for a complete transition to narrowband or to use a technology that provides similar efficiency, meaning 2 voice channels in a 25 kHz space. It is a common misconception that digital operation is required for narrowbanding. This is not correct. Properly licensed users are able to operate narrowband analog systems and obtain equipment capable of such operation.
Okay, I got that. Thank you, 10-4.
The narrowband deadline was finally presented as January 1st, 2013. Users operating at 25 kHz after this date are subject to fines and other penalties. However, certain users in the 470 to 512 band, also known as the T-band because this band was formerly occupied by television channels, was not required to narrowband pending the development of a nationwide broadband system. P25 Overview. Project 25, or more commonly referred to as P25, is a partnership between the public safety communications community and industry manufacturers. The P25 standard was originally developed as a group of standards to promote narrowband, digital, two-way, wireless communication. P25 products, systems, and standards are designed to meet the mission-critical needs of public safety personnel. The P25 standards were also intended to enable governments and the private sector to work with standardized, narrowband products and systems. P25 systems can operate in conventional or trunked configurations, and subscribers can operate in a simplex mode. The important thing to note is that P25 systems are narrowband compliant, and the technology is not proprietary to any individual company or system. You can buy, install, and use P25 compliant equipment from any manufacturer, and it would be expected to connect and work on your P25 system. This is due to the RF subsystem and the Common Air Interface, or CAI. The infrastructure equipment uses what is referred to as the RF subsystem. The RF subsystem uses P25 interfaces to allow the connection of various site equipment to support the intersystem interfaces and the call handling. The CAI is the common point within the equipment that allows for system operation no matter who provides the equipment. P25 trunking uses a control channel, and subscribers operate in either an implicit or explicit mode. In implicit mode, all subscribers are programmed with the channel and trunking frequencies. The radio then looks at its own list of frequencies to go to when directed by the control channel. In explicit mode, the subscriber gets its frequency information from the system. When the call is complete, the subscriber goes back to the control channel. P25 Phase 1 compliance meets the FCC narrowbanding mandate with 12.5 kHz operation. P25 Phase 2 compliance offers the capability of allowing 2 voice channels within a 12.5 kHz bandwidth or 6.25 kHz per voice channel. Future systems. The increasing demands for interoperability with other groups, services like video backhaul and mobile data, and the efficient use of frequencies and bandwidth push the development of technologies to the next levels. In 2009, the Federal Communications Commission was tasked to develop a national broadband plan to address national broadband issues, including the need to advance the use of broadband technologies for public safety and homeland security. In support of a nationwide broadband network for public safety, the Middle Class Tax Relief and Job Creation Act of 2012 was signed into law in February 2012. This authorized additional frequencies in the 700 MHz band, known as the D block, which increased the amount of public safety spectrum to support broadband data. The Act also provides initial funding to support the deployment of infrastructure and technology. Staffed with members of public safety and the private sector, the First Responder Network Authority, or FirstNet, is charged under direction from the National Telecommunications and Information Administration with taking all actions necessary to build, deploy, and operate the broadband network. As the technology develops, it is not quite clear as to where today's public safety communications technology will fit with broadband. However, public safety communications professionals working with private sector partnerships are diligently working to provide reliable public safety-grade technology and performance while providing interoperability and quality data services that will support our first responders.